Okay, let's start today with, we're going to start chapter 4. Chapter 4 is there's only one group of homework sections from chapter 4, so when I assign problems from chapter 4, it's all at the end of chapter 4. So we're going to be, this is the first time we've got enough information, we'll get some more definitions today, but we're going to start proving math statements, okay? And so that's kind of that is our goal for this class, is to learn how to write proofs of theorems, all right? So that's our goal, how to prove theorems. And so if a proof is like an essay, where you're trying to convince anybody who reads your essay that this statement is true. You think about like if an English professor assigns an essay, everybody should be different, right? I mean, if they're the same, there's an issue. It's called plagiarism, right? So, I mean, somebody's copying somebody else's. But in this class, I mean, these proofs might be 4 or 5 sentences long, and in some sense, all of our proofs will probably look the same, and they could be, you know, if this was an English class, I might say you guys all cheated or something. But there is kind of like for some of these more basic theorems, there's kind of like a clear way to go, and so in that way, all of our proofs will look the same, they'll almost be identical. Okay, for the more basic theorems. Now, when you get to higher mathematics, then they take different shapes and forms. But for now, really, we're going to have. I mean, if you all write 4 sentences, I mean, chances are the beginning and the end are going to be the same, and then you really only have some variation maybe in the middle. But we should have. So at chapter 4, we're going to start proving if-then statements using a technique called direct proof. Okay, so that's the goal of chapter 4. Learn how to write proofs of if-then statements directly, or using the method of direct proof. Okay, so our goal is to learn how to prove theorems. So chapter 4 is just direct proof, and the next section, the next chapter, we'll learn about how to prove statements using contrapositives, and then we'll learn some other techniques as well to prove math statements. Okay, the first one is direct proof. Now, so section 4.1 is on theorems. And the various names of theorems. Okay, so I'm gonna define some names, different names that people use for theorems. These are the things that we're going to try to prove, right? So a theorem is just going to be a math statement that is true. Okay. Now, some math statements that are true, like 1 + 1 = 2. That's a math statement that's true. Now, that wouldn't be elevated to the level of even calling it a theorem. So usually theorems, are think of like the Pythagorean theorem. You've heard that word, the Pythagorean theorem. Now, that's a theorem. I mean, that's something that's very useful, and it's a math statement that's true, but it's also pretty important. Okay. All right. So when I have a theorem. If it's true, then someone has demonstrated a proof of that theorem. So a proof, just think of it as an essay that incontrovertibly shows that a theorem is true. So if somebody reads this, there's no doubt that you've convinced that person that this statement is true. So that's what a proof is. That's our goal. Okay. So here's some alternate names for theorems. And you get used to these when the more math classes say. Different books use different names for theorems. Some books will call all the theorems and all of them. They'll call them all propositions. So this kind of just depends from book to book. But a general name for a theorem is a result. Like I have a very nice result that blah blah blah. People say a result is just a generic name for a theorem. fact. I've used that. I've used that in our class. Like I'll say fact. This is a fact. I mean, it's like 2 + 2 = 4. I mean, that's a math fact. It's just such a basic. It's just a basic math statement. Okay, it's a very, very minor theorem. I'm not gonna test you guys on these names. I'm showing you these are the type of things you'll see in your math classes when people refer to a fact or something. This is what it's a minor theorem. Proposition usually is a name for kind of some minor theorem. Like I said, I've had many books that instead of saying every statement that they have in the book calling it a theorem, they'll just say that for the big theorems, and then they use proposition for anything that's kind of more of a smaller theorem or a minor theorem. All right. Here's one you'll hear a lot. Lemma. You've heard that before in our math class. A lemma. A lemma is another name for a theorem, but it's usually a theorem. So you might have a whole a really difficult topic that you're trying to present in a book or something, and instead of making a whole chapter be one long proof, to organize a whole chapter, an author will break it up into smaller chunks. Okay, and so they might prove a lemma, and that lemma might be used later in another theorem, a proof of another theorem. That way, instead of having just such a really, really long theorem, you would just, in the middle of your proof, you would say, well, now due to lemma number 1.6, we have this. And so it's a theorem used to prove another theorem, a bigger theorem. Okay. So let's talk about this. Say this is a theorem whose main purpose is to help prove another more important theorem.
So would a definition be considered a theorem, or?
No. Well, it's a math statement. It's true, but that usually, you use definitions. Definitions are the building blocks that you're starting to write math statements about these topics that you define. There's certainly a connection. You usually define terms in math class. You can define a bunch of terms. Like today, we'll define a bunch of terms, and then we'll say we'll prove statements about those using those words that we just defined. Okay, we'll talk about what does it mean for an integer to be even, and then we'll say something about a theorem about even numbers. Okay, so lemma is a theorem whose main purpose is to help prove another, say, more important theorem. Okay. Again, it's kind of like an organizational tool. Instead of having just this huge theorem with lots of sub-theorems and proofs, you would an author would organize their chapter. They have a lemma, and then they prove a theorem, and then in that theorem they may refer back to the previous proof. Say, well, by lemma of 1.6, we have we can use this in our new proof. Okay. All right. So lemma usually comes before a big theorem. There's another type of theorem that comes after you prove something, and it's called a corollary. A corollary is a theorem that is an immediate consequence of a previous theorem. Okay, so these are, oftentimes how new math is created. Somebody will take somebody's theorem and then they'll see if they can extend it somehow to something more powerful. And so a corollary is kind of like that. Like, well, you have a big theorem, and then you say, oh, okay, well, because of that, now I can assume this is also true. And so that's a corollary to the previous theorem.
So, how some are using like the second law, how many different directions you can go with using that argument the second law to.
Yeah, or you could say, like, if you have a really broad theorem, and then maybe a special case of that broad theorem that's useful somehow, you say, okay, well, this is a corollary of this other theorem. This one you almost don't even need a proof of this, because it could be like just a special case of the previous theorem, or this becomes very obvious because you have proved the previous theorem. So it follows right after a bigger theorem. We call that a corollary. You've heard that word before, corollary, maybe? Again, you'll see these. The more math class will take you. Anytime you guys take an upper level, like analysis or algebraic algebra, you'll definitely see these words. And then I had a professor in grad school who called this a corollary. And the whole semester was just like freaking out. Like, no, it's a corollary. I mean, this guy was, obviously he's a great mathematician, but I never heard that before. So I say corollary. Okay. And then another small theorem is what we call a claim, and this is usually reserved for. It's again another kind of organizational type of theorem. Again, if you have a really big theorem, you can have like different kind of like pieces to your theorem, and instead of, okay, here's my big theorem, I'm going to prove this first part, blah, 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 you take like a paragraph, then I'm going to prove the second part, another big paragraph. Like oftentimes you can just you can have a claim, and it's kind of like a sub-proof inside your big proof. Okay, so you say, okay, I'm going to use this claim. I'm going to use this little theorem in my proof, and then you have a little sub-proof of the claim in your big proof. Okay, so it's very similar to a lemma, but whereas a lemma comes before the big theorem you're going to use it for, the claim is kind of in the middle of the theorem you're trying to prove. Okay, so it's similar to a lemma. But the claim usually appears inside a proof. Of a larger theorem. Okay, so these are some common names for theorems. Okay, and if we had picked one topic, like if this was a number theory class, you would see this over and over again. You say like theorem 1, theorem 2, theorem 3, and then corollary 1, corollary, and so you'd see these words more often in a more cohesive like topic class, like number theory or algebra, real analysis. Okay, so we studied conditional statements a lot. We looked at if P then Q. The truth tables we looked at equivalent statements like the contrapositive, not Q implies not P. We looked at what does it mean to negate. And so we spent a lot of time on if-then statements because a lot of math theorems are in the if-then form. Okay, so theorems often have the conditional form if P then Q. Okay, so we're going to learn a few techniques to prove these type of statements. A direct proof is the first type. As we'll see today, I'll do some examples. A direct proof of an if-then statement is you start with this hypothesis, the P statement. You assume this P statement is true, and then you show that forces the Q statement to be true, the conclusion. Okay, so you just start with this and go just work from the definitions to show that this statement is true, and that's called the direct proof method. Okay, so that's what we're going to first look at in chapter 4. Okay, before we get to proofs of these type of statements, we're still going to need some more information, some more definitions, and then once we have more definitions, then we can make these statements and then hopefully prove them. Okay, so let's start over with some definitions. Erase this here. All right. So 4.2, these are some key definitions that we're going to need. Here's the theorem. The sum of two even integers is even. So I say this is a theorem, so I'm kind of already, just since I define a theorem as a math statement that's true, I'm claiming this is true. Do you guys believe this is a true statement? From your experience with integers, you add two even integers, you get something that's even. Right? Okay. Prove it. Well, you might, oftentimes when students are just first asked to prove a math statement, they'll often give an example, like, okay, well, 2 plus 4 equals 6. Even plus even equals even. Therefore, the statement's true. An example is not a proof.
So can we split it up in an and statement?
Well, this is, you think about it. I said many theorems are if-then statements. I would think of this as a conditional if-then statement. So we're going to prove this statement today. And the way I would think of it as an if-then statement is, if I have two even numbers, so let's call them x and y. If I have two even numbers, x and y, then x plus y has to be even. So that's how I would translate this think of this as an if-then statement. So that's how we're gonna prove this statement using a direct proof. And one example does not a proof make. We're talking about the sum of, any two even numbers. So just because you show me it works for these two, I add these two and I get an even number, that doesn't mean that it's going to work for every even number. This is not a incontrovertible proof. You can't say, well, how does that show that for every even number? In the first place, what do I even mean by even? I haven't given you a precise definition of even yet. So what does even mean? Divisible by 2? Is that how everybody would say the same thing? I said, if you ask say a kindergartner, they can learn about even and odd. So kindergartner, an even number is divisible by 2. What would they ask you if you told them that? What's divisible? Now, what is divisible? So I agree. Every even integer is divisible by 2. I agree with that statement. But it's kind of like if that was our definition, then we kind of have to define divisible too, right?
Make a multiple.
It's a multiple. So maybe a multiple of 2.
No.
Every integer is a multiple of 2.
Like 2n.
Okay. So there's the number 2's involved.
Yeah.
Right. Now we all agree the number 2's involved for even. So I have a son who's in kindergarten, and he told me he defined even and odd numbers for me. Because he figured this out on his own that for even numbers, you can put them into two different piles. Like if you have an even number of blocks, like say you have 6 blocks, you can put you can split them up into two groups. But if you have an odd number, there's always going to be a middle one. Instead, like they say you have 7, I mean, you can't. There's always going to be like this odd man out. You can't divide them up into 2 different groups. And so that's kind of the idea, right? Like if something's even, there's a factor of 2 here. This is like 2 times 3. But for odd, you can't do 2 times 3. I mean, well, if you do 2 times 3, there's still this 1 hanging out left over. So it's kind of like 2 times 3 plus 1. And that's kind of how we're going to define even and odd. So we're going to have a very precise definition here in a second. But what, like this statement, what about if somebody just read this? Does everybody know what an integer is? Just Joe Schmo on the street, do they know what an integer is? I mean, we've already talked about integers. So at some point, you're going to have to. You can't just keep defining every single word. I mean, we're going to have to start with the basis of things like our sets of numbers. So we know what integers are. We're not going to have to define integers anymore. We know what integers are. We know what real numbers are. We know what rational numbers are, for example. Okay, but things like even, I mean, this does need a definition. Okay, so here's our definition for even. An integer n is even if n equals 2 times a for some integer a. So this is important that some of these definitions, I mean, you're just going to have to memorize, because if we're going to use definitions in our proofs. So if I claim that something is even, then you will say to yourself, okay, I know what that means. That means that n can be written as 2 times an integer, some integer a. Okay? So convince yourself, if you have any even integer, you can write it as 2 times some other integer. Okay? All right. Definition. An integer n is odd if n equals 2 times a plus 1 for some integer a. So you think of odd as being 1 more than a multiple of 2. So think about it. Any integer you can think of is either even or odd. It's either a multiple of 2, and this is one way of saying it, or you can write it as 2 times an integer, or it can be it's 1 more than 2 times an integer. Okay, that's how we're going to define even and odd. So one of the key parts of direct proof is you're given some words. You use the definition of that word in like one of your first few lines of that proof. You just unravel these definitions. Okay. Now definitions, I think I mentioned this before, but definitions are technically they're biconditional statements. Like n is even if and only if n equals 2a for some integer a. And some people will actually write them as if and only if statements, but majority of the time it's really just a conditional statement, like if p then q type sentence when you write a definition. But I mean, technically, I could replace this if with if and only if, and if and only. I mean, these are definitions are really supposed to be biconditional, but and the author does this. He mentioned this in a paragraph. He usually just sticks to an if-then statement for definitions. Okay. All right. Another definition. So these are some words that you'll see in theorems. So when they say 2 integers have the same parity, they're the same parity, that means they're both even or they're both odd. Okay? So 2 integers have the same parity. They are both even or both odd. Okay. Otherwise, we say they have opposite parity. So again, some words that you'll see in some theorems. Okay. Parity. Okay. Here's the theorem I mentioned before. Oh, it's a stone word. Okay. The sum of two even integers is even. So let's look at a direct proof of this statement. Okay. Now we have a precise definition of even. I'm going to kind of rewrite this as a conditional statement. That's often the way these theorems appear. Okay. So our first proof will be if-then statement. Let me rewrite this using if-then statement. So here's the statement to prove. Prove if x and y are even integers, usually from the context, when you say something's even, you're assuming, it's an integer. So, you really probably didn't need to say the word integer. It's assumed we're talking about integers. Okay, so if x and y are even, then x plus y is even. Okay, that's what I said. I want to prove. The sum of two even integers is even. Okay. So when you're given a theorem, you have a theorem, you write the theorem out, and then to signify you're going to give a proof, you write the word proof. You write the word proof, sometimes abbreviated PF, but you signal to somebody, I'm about to prove this theorem. Okay, you give them a signal, you're starting it. And oftentimes you use a signal to show that you're done, okay? Because if you have an essay and it stops, and then especially if you're writing in a book, you often want to let the reader know, okay, we're done with the proof. Now we're going back to just regular chapter or regular exposition. So there's a couple of ways. The book is fond of using a little square at the end of your proofs, and there's other ways. Another kind of historical way is to write the letters QED. And I was kind of researching this yesterday. That QED, I looked at some old manuscripts of mathematics, even back to like 1600 and stuff, and they often would write this. A lot of stuff was I guess most academic material was written in Latin until even through probably 1700s. I don't know, but then a lot of work was done in English, England, Germany, and France. So those became kind of common languages. Now, really, English and France, English and French are still really popular, but English has kind of come on top of the list of languages. But QED stands for a Latin phrase, and it basically means that which was to be demonstrated. Okay, so you finish up with. So we're going to start off saying something that x and y are even, and our last line is going to be something like x plus y is even, and we'll say which is what we're going to try to show. That's what so we're done. We finished showing what we tried to show. Okay, it stands for quad. Let me write it out here. Erat. Yeah, I'm looking up on erat demonstratum. I don't speak Latin. Quad erat demonstratum. Random. And so I look at a manuscript from the 1600s, and a guy who actually wrote quad erat demonstrandum at the end of each proof, but that got shortened to just QED.
I think
I would use more than
colored in dots.
Yeah. Well, you take that, colored in square, but the book uses squares to symbolize the end of the proof. You wouldn't use both of them. You use one or the other. I usually reserve QED for a long proof. This seems like to me more prestigious than this stuff, a little box. So I'd use a little box, but if it's like a really big thing, you're like, yes, QED, we did it, you know. So that's how you symbolize, you know, show somebody that you're done with your proof. Okay? All right. There's our proof. So remember, we're using a direct technique here. All right. So I'm going to start off assuming this hypothesis. I'm going to assume that I have two even integers, x and y. Okay? So you start off with the words like suppose x and y are even integers. Some people like to say assume, but you assume that you have this statement as true. So you say suppose. I mean, this is where there's a little bit of stylistic difference. Some people use different phrases, different words to get started, like assume or suppose. Some people use therefore. Some people use thus. But basically, we'll have the same proofs. All right, so suppose x and y are even integers. So this is very common. I mean, this is how a direct proof starts. You assume the hypothesis. Okay. You should be able to write the first sentence and the last sentence of a proof using, well, of any if-then statement. But for a direct proof, you could write the first sentence, you could write the last sentence. The last sentence you should end up with Q. So x plus y is even. So probably, you know, if you want to kind of leave some room, if you're doing these from the start, you know, you could say the last line might be therefore x plus y is even. So it's kind of like you can start this proof actually from both directions, from the start and from the finish. So that's what the end of my proof should look like. Okay. Oftentimes you can start with maybe like one line, one sentence on each line. But then if you're doing your final draft, right? If you have these drafts of your essays, it might just become a long paragraph at the end. Okay. All right. So suppose x and y are even integers, and then we're done when we can conclude that x plus y is even. All right. Now I'm just going to unravel the definitions, and now I can actually work from both ends of this proof. All right. So I know x is even. Let's use our definition. We know that if a number is even, I can write it as 2 times some integer. Okay? So let's say, since x is even, I'll say something like, well, then x equals 2 times a for some integer a. So I'm unraveling the definition of even. I'm going to do the same thing for y. If I know y is even, but here's something, you can't use the same letter a. A stands for some arbitrary integer. So you got to use a different letter to stand for, because you know it could be a different integer for y. So similarly, y equals 2 times, let's say b, for some integer b. Okay? So that's why we need to have precise definitions so we know exactly, you know, when we're saying something. You know, have someplace to go. I mean, you just start with the hypothesis, use your definitions, and think about like the line right before the end. If I can conclude that x plus y is even, what should the previous line look like? Yeah, x plus y should look like 2 times some integer, right? So you can even like kind of write this. I mean, it's good to often write in pencil when you're writing your proofs. But what were you going to say?
I was going to say the next time after y equals 2b, you have like then x plus y would be equivalent to 2a plus 2b.
Yeah. So that's where we're going, and I'm trying to show you that just knowing the definition, you basically have the whole proof written. And there is going to be some. We still have to do some work in the middle to link the two halves together. But you could kind of write this whole theorem just knowing the definition of even. So, well, if I can conclude that x plus y is even, then x plus y should look like 2 times some other number. Now, I'm going to use A and B.
C.
Yeah, let's use C. I mean, this is very common. A, B, and C, letters at the beginning of the alphabet are often, constants that you're using. So then x plus y equals 2c for some integer c. Okay? And there's still this gap in the middle. We need to get from these definitions to this one. You have to kind of forge a link between the two halves.
C would be equivalent to A plus B.
Yeah, some of you can see it. Like if I have a statement about x and a statement about y, and then here I have a statement about x plus y, then why don't I add these two equations together? So you're going to just use like your basic math knowledge, your addition or whatever, to forge this link here in the middle. So let's try that. So let's try adding these together. Add these two equations together. So x plus y equals 2a plus 2b. Okay? But think about this, right? I have to get this side to look like 2 times an integer.
So we have to factor out 2.
Let's factor out that 2 there. So exactly. So we just use addition. Now we're going to use factoring. One thing with equations, oftentimes you can kind of just make a chain of equations. You can make a whole new line. I might even just, instead of saying then x plus y equals 2 times parentheses a plus b, you could just let's just do it here to make a chain of equations. Okay? So then x plus y equals 2a plus 2b, and you don't even really need to say anything here because, I mean, this, you should assume that anybody reading this would know exactly what you just did. Right? Like from here to here to here, they should know what you just did. Here, if it should be obvious, okay, they're factoring out of 2. I mean, maybe it's not obvious to some people who don't learn the algebra, but I mean, for people reading these type of theorems, you can assume that this is true without saying, therefore, by the distribution property of, you don't have to say that, just do this. So now, do you see this looks like 2 times a plus b. It looks like 2 times an integer, right? I mean, this is 2 times a plus b.
One integer plus another integer equals another integer.
Yeah, it's kind of, there's kind of something there maybe needs to be said, right? Can you assume if a is an integer and b is an integer, can you assume that a plus b is an integer? Is that true? It is true. And so that's one of the things I'm going to allow you guys in your proofs. You can use that fact without having to say it every time. Like, so if you add 2 integers, you get an integer. Okay? You say, fancy way of saying it is the integers are closed under addition. It means if you add 2 integers together, you get an integer. Okay? Same thing with subtraction. If you subtract 2 integers, you get an integer. What if you multiply 2 integers? You get an integer? Yeah, so you can multiply. What about division? No. So you cannot assume, like if it was a divided by b, you can't assume that's an integer. You can assume it's a, what?
Rational.
It's rational, right? That's the definition of rational. It can be written as the fraction of integers. So for this point, I'm not going to have to say that the sum of 2 integers is an integer. Okay? All right. So we're pretty much done. I mean, can I just say, am I done really though? There's maybe I need to say a little bit more about like right here, right? Yeah. So we do have x plus y. It looks like 2 times an integer, but I changed it to c. So I better say something about c. Maybe I should add something here. How about then x plus y equals 2c for some integer c. Let's say c equals a plus b. Now it kind of fully, connects the two halves. All right, we wanted x plus y to look like 2 times an integer. We pretty much got it there, 2 times a plus b. So as long as we say that c stands for a plus b, then it should make sense. Okay. So let's see here. So let's read this. So suppose x and y are even integers, and x equals 2a for some integer a. Similarly, y equals 2b for some integer b. Then x plus y equals 2a plus 2b. which equals 2 times a plus b, then x plus y equals 2c for some integer c equal to a plus b. Therefore, we can conclude from this statement that x plus y is even. Yeah. Any questions?
Did you put the integer for like the c equals a plus b on its own line?
Sure, yeah. Yeah, you can say, so you can say like, let c equal a plus b. Then x plus y equals 2c for some integer c. Yeah, sure. And that's where there will be some stylistic differences, but for the most part, I think everybody's proof would pretty much look the same. You'd unravel definitions, so you'd have somewhere you'd say x is 2 times an integer, y is 2 times an integer, and you'd show that x plus y equals 2 times an integer, and then you conclude x plus y is even. Okay? So we wrote the hypothesis, we wrote the conclusion, we unraveled the definitions. You can really do this. When you're starting out, you can if you get stuck, you don't know where to go forward. Maybe try to go from the back, So to unravel the definition here, and then maybe you can see what needs to be added in the middle to connect the two halves together. Okay. So this is an example of a direct proof. I just used the definitions in the hypothesis to conclude the conclusion. Okay. So let me just be more specific about, I mentioned this. A plus b is an integer. Okay. So from now on, I'll let you assume that integers are closed under addition, subtraction, and multiplication. So I'm going to write that. So here's a fact. Okay, so you can use this in your proof. But you don't have to say that every single time. So suppose a and b are integers. Then a plus b is an integer. A minus b is an integer. And a times b is an integer. Okay. Again, it's a fancy way. A fancy way to say it would you say the integers are closed under addition. The integers are closed under subtraction. The integers are closed under multiplication. So that's the way you might say it in you take abstract algebra. You might hear those kind of words. Okay. A set is closed under an operation if you take two objects and you use that operation and you still have one of those objects. It's closed under that operation. Okay. So you can also combine all these, right? Like if I had an expression like a squared b minus 3a plus b. Can I assume this is an integer?
Mm-hmm.
If a and b are integers, well then a squared is an integer. That's just a times a. A squared times b, that's an integer times an integer. Subtract 3 times a. Well, 3 times a is an integer, so if I subtract an integer from an integer, I get an integer. Add an integer, so you can combine that. Combine all these. So if you have, you'll see. I'll give you. I think a proof for homework where you have an expression that's more complicated, but all the pieces are integers, and you're just adding, subtracting, multiplying. So the result is still an integer. Okay. So this is a fact you can use without saying. Like right here, I just said that a plus b is an integer. I didn't have to prove it or anything. Okay. Any questions so far? All right. So we got 3 definitions so far: even, odd, and then parity. Let's talk about division. We came up a little bit earlier. Like, what does it mean that an even number is divisible by 2? We'll define that now. Let's talk about what does it mean to be divisible, or one integer divides another. You just need a break. Let's take a Let's take a break. 2 minutes. Everybody write this down.
Then I use the eraser app. Fake eraser. Oh my god.
It will be, I mean, it's not that. Yeah, or,
I use
Monday, yeah.
emotional.
I don't know easy how it works. Not on Mondays.
Definitely as soon as possible. One that I call it not very much care for.
Yeah.
It's like you wait for that for
Like I hate these. Oh yay! The only reason I don't like it is because this comes off on your fingers. The shiny stuff? Yeah, so your fingers get shiny colors. They're pushy, I think. Yeah.
It looks like regular things.
Oh, the blue one. See, the color comes out. Oh, you know, right? It annoys me. You keep the blue one. You can keep the blue one. No. I wonder if they do you want one? We can all be twinsies. Shut up. I have these ones that are, there's this one I like in particular, because I feel like for some reason every time I use it, I do well on everything. It's green, and it, you know, it has squishy pin on here, but it has all these flowery designs on it. Oh, so pretty. That's why I like it. No. This is
Oh, so I think colors you have warm colors.
Oh, back. Let's continue. All right, here's another definition. So senators and B. We say A divides B written. Now this is important, a distinction. I mean, you're used to seeing fractions with like a slanted line for like the division symbol. So this is not A over B. Don't think of it as, it's not written as a fraction. This is a vertical line. It's kind of like an absolute value line, you know, straight up and down. Okay. So in your proofs, make sure you use a vertical line to, this symbolizes A divides B. Okay. So we say A divides B. If you can write B as A times an integer. So A divides B if B equals A times C for some integer C. So does it seem kind of weird that we define division, kind of division, define it by multiplication? Technically, I mean, if you look at like any college algebra book that defines division, it actually says they define division as the multiplication by the inverse of a number. So, like instead of saying B over A, you define B over A as B times 1 over A. When 1 over A stands for the inverse of A. So, But so this is how we define when we say A divides B. So when we talk about what does it mean for something to be even, you could say it's divisible by 2, or 2 divides that even number. So think about it. If I said 2 divides an integer, then I could write that integer as 2 times c. So that's, it matches up with our definition of even. So it could be equivalent to saying, if you said even integer is an integer, if 2 divides an integer, then that integer is even. Okay. Some other things we say, so, we say if A divides B, we call A a divisor of B. Okay, so we say A is a divisor of B. Sometimes you see a factor. So A is a factor of B, or A is a divisor of B. So it's kind of equivalent to saying that A divides B. Another thing we say is B is a multiple of A. Okay. Kind of define the other words, but they're all connected here. Right? If I said A is a factor of B, then I could have just as easily said B is a multiple of A. Okay. So 3 divides 12. That's how you would read this. 3 divides 12. Because, well, can I write 12 as 3 times an integer? 3 times 4. So 3 divides 12 because 12 equals 3 times 4. So you put a slash through something, that's like slash through an equal sign means not equal to. So this means that you would read this 5 does not divide 12. 5 does not divide 12.
Because C is not an integer.
Well, because there does not exist an integer C where 12 equals 5 times C. Another way of thinking. So because you cannot find an integer C where 12 equals 5 times C. Okay. Let's do a proof using this new definition of divides. Prove if 8 divides n, then 4 divides n. Does that statement sound familiar? We had some of these words, like if an integer is divisible by 8, then it's divisible by 4. That's really the same sentence, right? If an integer is divisible by 8, then the integer is divisible by 4. Okay? Proof. So again, I'm going to model a direct proof. So when I started my last direct proof, I'm going to assume this first statement. This is the hypothesis. So I'm going to say, assume 8 divides n. My conclusion, well, it's going to end down here, then 4 divides n. And that'll be, that should be my last sentence. Okay, I'm going to unravel these definitions now. So by definition of dividing, 8 divides n. And what does the definition tell me? N equals
some C that's an integer.
Yes, so if 8 divides n, then n equals 8 times some integer. So I haven't used a yet, I'm going to start with a. So n equals 8a for some integer a. Okay, you don't have to start with c, but you can be c if you want to. Any questions about that unraveling of that definition? So 8 divides n, that means I can write n as 8 times an integer. And I chose the letter A to stand for that arbitrary integer. What is the next to last line going to be? If 4 divides n, then kind of think similarly, right? N equals 4 times some integer. Let's say b. N equals 4b for some integer b. Okay? So now I've unraveled the definitions. I need to get from n equals 8a to make it look like n equals 4 times b.
Have something like 8a equals 4b.
Yeah, so the 8a is I'm gonna have to rewrite this 8a as 4b. So can you tell me? I mean, you realize that there's a factor 4 in here, right? And that's kind of like I need to pull that factor 4 out to the front. This 8 has a factor 4 in it, right? 8 is 4 times 2. So if I recognize that there's a factor 4 here, I just need to pull it out. I'm gonna factor this number 8. That's really what I'm gonna do. Then n equals 4 times 2a. You think of it that way, right? Basically, I'm just factoring the number 8. That's 4 times 2.
Can we say 2a?
Mm-hmm. Yeah, so this looks like 4 times an integer, right? Because if a is an integer, 2a is an integer. So that's what my b is going to stand for. Since then n equals 4 times 2a, I can even write it like this. Then n equals 4 times 2a, which equals 4b. For some integer b equal to 2a. And I don't even really need to say anything else. I mean, I've already got, I could go to the next line. Then 4 equals n, then n equals 4b for some integer b. Therefore, or then, or thus 4 divides n.
If we have the for some integer b equals 2a, do we need it in the line below it as well?
Well, you remember how, you can refine your proof like kind of at the end. It's kind of a rough draft. But when I went from this last line up to here, that's literally what the definition was, right? And so yeah, if you've already, you might kind of streamline your proof a bit if you instead of saying that over and over again. Yeah, most of the time, if I was going just straight from the top to the bottom, I probably would have just left off, then n equals 4b, and then it's, in a number theory class, like an upper level math class, you would just say you're done like that. Therefore, 4 divides n. Okay, so you would almost once you get more sophisticated, you wouldn't have to even have this. But technically, I want you to be very precise right now. Go from to conclude this, you'd have to have a line right now of exactly what this means. Okay. And it's also the idea of starting this proof. If you get stuck with this, sometimes this middle section can be kind of like, well, I don't have no idea what to do next. Well, to get you kind of going, start from the bottom and work up. And then maybe you can see, okay, well, I have this 8a, and I need to make it look like 4b, so that's where I need to do my work. I need to think about that. Okay. So once you get your proof done, you probably could have rewritten it again to make it more streamlined. Any questions? Any other questions? All right. Time for another definition. You guys like definitions? You'll love like abstract algebras. A bunch of new definitions and much proofs using those new definitions. But we'll use these same definitions over and over and over. So, this isn't like I said. These are topics from a number theory class, but it's just so we can get practice writing proofs. All right. A natural number say n is prime if it has exactly two positive divisors, 1 and n. Okay. So this is going to be our definition of prime. I mean, it's probably the way you've thought of number prime. Like you can't factor a prime number other than trivial factorization. And 1 times then, like 7, the only way you can factor 7 is 1 times 7. There's no other positive divisor. I mean, you could factor it as -1 times -7, but those aren't positive divisors. Okay. Number is prime. It has exactly 2 positive divisors, 1 and 1. Okay. I don't know if you thought about this, but say is the number 1 prime? So let's look at the definition. If I said 1 is prime, then that would mean there's exactly 2 positive divisors, 1 and 1. But 1 and 1 is that's only 1 number. So it only has 1 divisor, 1 positive divisor. So 1 is not prime. Does it seem kind of racist against 1? Poor fella, it's just so small. Or maybe it's like height discrimination. It's like he's so tiny, he's not prime. You know, that's his problem. I mean, he doesn't have more than 2 divisors, right? Every other natural number will have at least 3 positive divisors. Or 1 has only got 1 positive divisor. Right? So 1 is not prime. Okay. All right. So here's a fact. Every natural number greater than 1 is either prime or composite. That's the other, almost the other half of the coin. So you can't say every natural number is either prime or composite. It's not quite the same as even or odd, because that number 1 messes it up. I mean, 1's a natural number, but it's neither prime nor composite. It kind of messes it up when you talk about it. You cannot just say, if I said, I'm thinking of a natural number and it's not prime. You can't say, okay, well, it's definitely composite. Because I could have been talking about the number 1. Okay. All right. So every natural number bigger than 1 is either prime or composite. So I haven't really defined composite. How would you define the word composite without looking at the book?
Composed of multiple, a natural number that has
Composed of multiple.
has multiple positive divisors.
So like 2.
Sure.
So prime numbers have 2, so that's multiple. Right? Is that what you mean? Do you really use the word multiple in this definition? Okay, greater than 2. Okay, sounds good. So a composite number would have at least 3, maybe, so more than 2 is what you're saying. Has more than 2 positive divisors. That sound reasonable?
Sure.
So, but whatever, it's really you're saying there's some other divisor that exists. It's an existent statement. There is another positive divisor other than 1 and n. Right? I mean, 1 and n are going to be positive divisors of any n. But we have two. We know for sure one is a divisor of every natural number. N is a divisor of itself. But there's another one. Yeah.
You say there exists a number between 1 and n that divides n?
Yeah, that's pretty much the textbook definition. There's another one, and in particular, it's a number other than 1 and n. So it's between 1 and n, and it divides n. Okay, so here's our, let's say, our textbook definition of composite. So a natural number n is composite if how would I read that phrase? If there exists an integer b, right? Such that b divides n. So okay, there's another divisor. Okay, I haven't said anything new. I mean, every integer so far, every natural number so far satisfies this definition. It has a divisor, but there's something special about the divisor. And the divisor is strictly between 1 and n. Okay, so now we have a third divisor. So a number n is composite if there's another divisor.
Why can't we say
B, or b is between 1 and n.
Why can't we say b is less than or equal to n?
That doesn't force it to have more than 2. You could be talking about 1 and n, because n is less than or equal to n. But we want another one. There has to be, so 1 doesn't satisfy this inequality, n doesn't satisfy this inequality, so there's another one. There's at least a third one, the third divisor of n. Okay, and some composite numbers only have 3 positive divisors. Give me an example of a natural number who has 3 positive divisors, exactly 3. 4. 4? What are the divisors? 1, 2, 4. Anyone think of another one? 9. The divisors are 1, 3, and 9. So what do 4 and 9 have in common? A perfect square. Yeah. So perfect squares often only have, well, not every perfect square has exactly 3. Like 16 is a perfect square. It's 4 squared. But it has more. It has 1, 2, 4, 8. Yeah. 15. Yeah. So if it was a perfect square of a prime number,
That would have 3.
then it would have. Is that a theorem? Yeah, maybe it's a theorem. So I mean, that would be a theorem, right? You could say that so if n is the perfect square, if n equals p squared for some prime, then p has exactly 3 divisors. That's a true statement. Okay. Positive divisor. All right. So that's so we got all our definitions. Let's talk about, so 4.3 talks about just more abstractly about just the method of direct proof. Okay, so we've really covered 4.1 and 4.2 now. If I can bring this around. Okay. So let's talk about, so 4.3. I want to be more precise about the steps to produce a direct proof of an if-then statement. So 4.3, direct proof. All right. So here's kind of an outline of a direct proof of a conditional sentence. And if P, then Q statement. Okay, I've tried to model this twice already today with 2 proofs. So what I did was I assumed the hypothesis, the P statement. So first, write the first sentence of the proof, restating the hypothesis P okay, so that's where I said if X and Y are even. So I assume my first sentence was suppose X and Y are even, or assume X and Y are even. Okay, so you write your first sentence of the proof, restating the hypothesis P. Now, by the end of the class, you probably just continue your proof straight down. But for now, to get you started, if you write the first sentence, you should know what the last sentence looks like already. The last sentence is going to be therefore Q, or thus Q. So you can actually write the last sentence of your proof as well. So you can write the last sentence of the proof by restating the conclusion Q. Now, you say something like therefore Q. And, if I'm writing proofs, I don't like to erase everything or do everything on a scratch piece of paper and then transfer it over. So this is why, almost like in real practice, you might think about this last sentence instead of actually literally writing it out. Because you might need too much room or not enough room. So
would it be okay if we did our steps 1 and 2 and then started writing our proof so we knew what our hypothesis was and then knew what we were trying to get proof?
Yeah, that's my idea. These are steps. First, write your first sentence. Second, write your last sentence. And then you're going to kind of fill in. You can fill in from both ends. The next step, you're going to unravel the definitions. Okay. So step 3, unravel the definitions. Working forward from the beginning. Of the proof. And you can actually work backwards from the end. This is what I did in my 2 proofs today. Just unravel the definitions. Now you're kind of working from both ends, and then the last thing is you got to forge a link between the 2 halves. So using your knowledge of mathematics, and just, for now, your knowledge of integers and addition, subtraction, multiplication, primes, you're going to forge a link between the 2 halves. Okay? All right. So step 4. Try to link the 2 halves together using logic and standard math facts. So like one of the ones we had was recognizing 8 times an integer as 4 times, 8 to 8, we recognize that as 4 times 2a. So just using your knowledge of factoring or addition, subtraction, or distributive property or something. Okay. So a proof you can prove if-then statements other ways. When we get to chapter 5 on proofs by contrapositive, it will not look like this. These are not the steps that you would use to prove a statement like that. Then we'll look at proofs by contradiction. So it will not look like this. These will not be the steps you would use to solve a direct prove that statement using contradiction. Okay, so this is the first technique. This is like kind of the most straightforward. You start with P, unravel the definitions, end up with Q. Okay. You know, and if you follow this kind of guidelines, you might have to use an eraser and actually kind of, you know, maybe you left too much space, maybe you didn't leave enough space, maybe, you know, and then if you write one line and the next line, the next line, the next line, and that's not how you write essays, right? And for English, one sentence goes right to the next one, and then you know the paragraphs wrap around. So you can do that too. When you in your final draft, you would, if you're going to try to like put a proof in a book, you wouldn't write one sentence and then hit enter and then write the next sentence. I mean, you would just write it as a paragraph. Okay, so you might have to rewrite your proofs. Again, you want it to look real pretty. Okay. You have time for a proof? All right. Prove. If x is an even integer, then x squared is even. Okay. Proof. And I'm just going to show you like some. You do proofs often enough. You can write the word proof. Oftentimes I'll abbreviate it PF for the start of my proof. Okay. A lot of kind of the slang of proofs and just kind of it's okay to use, but I'd like you to, if you guys have practiced writing proofs before, try to humor me by showing all the details. When you get more used to proofs, you don't have to write out every single detail, but let's be very precise right now. Okay. All right. First step, I need to rewrite the hypothesis. So what should I write first?
Assume x is an even integer.
So we got assume or suppose, right? Either of those are acceptable, right? So suppose x is an even integer. I don't know. I like the word suppose instead of assume. It doesn't matter. It's just either one. All right. What's the last sentence going to be?
X squared is even.
Therefore, x squared is even, right? I mean, these some kind of like something like therefore or thus or thusly. How about therefore x squared is even? Okay. You don't have to write it squared if you don't want to.
X squared is equal to x times x.
Well, is that what the definition of x squared is even means?
Not quite.
So we did our first step, wrote our first sentence or our last sentence. Now let's unravel the definitions. What does it mean for x to be even?
Like equal to A.
Yeah, then x equals 2a for some integer a. Yeah, that's exactly. So I mean, x squared. I didn't define exponents, but x squared, you should know it means x times x. I mean, like you said, but I'm not going to define. I'm not going to use the fact that we're talking about x times x. I'm going to use the fact that x squared is even. What does the word even mean? So in the previous line would look something like then x squared equals 2 times b, right? For some integer b, right? That's the definition of x squared being even. Okay? All right. So I have an equation involving x, and an equation involving x squared, and this is that last step. I need to link these two halves. So how can I change an x to an x squared? Yeah, I can square both sides of the equation. Let's try that. Okay? So then x squared equals, now here's where, is that right?
No.
What do I need? What's wrong with it? Yeah, you gotta use parentheses, right? I mean, so you gotta know your exponent rules pretty well. And this is, I'm assuming you guys are, are good at math and you know your exponent rules. That the quantity 2a squared. Now, let's see. So I got the left-hand side fine. The right-hand side, I gotta get it looking like 2 times an integer. I mean, there's a factor here. Am I done? Does this look like 2 times an integer?
What have you done for the 2a squared?
Yeah. So we need to kind of multiply this all out, maybe, or somehow. This 2 is not the same as this 2. This 2 is trapped inside parentheses. So I need to use my exponent rules to get rid of these parentheses. So how would you rewrite this without an exponent? Oh, sorry. Well, you can't do it without an exponent, but without these parentheses is what I meant. So 2 gets squared and a gets squared. So it's 4a squared.
Would it be more, would it be better to write it as 2 times 2 times a squared, because then you already have your 2 times.
You could, but typically when you distribute an exponent, I probably wouldn't write. I might write as 2 squared, but it should be obvious that if I wrote 2 squared, I don't know, if I wrote 2a to the quantity squared, and then the next line I wrote 2 times 2. Do you see how somebody might say, well, wait a second, where did that extra 2 come from? So it seems like that's might be a little bit. I mean, people who are good at math wouldn't have a problem with that, but really, I want it to be very obvious what I did. So what I did was I squared the 2 and I squared the a. I mean, when I think back like an algebra class, that's how I would tell my students to distribute an exponent. I mean, it's not, like you said, it's not necessarily wrong. It's just I want it to be very obvious. So if it's not very obvious, then you might say something, add a little phrase. So we're getting close. There's a factor 2 right there, but it's inside the 4. So what should I rewrite this as? 2 times 2, and then I still have my a squared. And I'm really putting the emphasis there with the you might even write it as like 2, and then some people might even do this, like write it as like 2 times parentheses 2a squared. Just real emphasizing the fact that this looks like 2 times an integer. Remember, we can again, you can assume that 2a squared is an integer without saying it, because this is just multiplication, right? All right, are we done?
I was going to say p equals 2a squared.
Yeah, so I mean, we got it. I mean, it's 2 times an integer, but here I use the letter b for this stuff. So maybe I should say that right here. Right? So then x squared equals 2b for some integer b, and equal to 2a squared. Now, I believe, some people might write here equals 2b for some integer b, and then b equals for some integer b equals 2a squared, and then in the next line you'd say then x squared equals 2b for some integer b. Okay. Therefore, x squared is even. So there's really, I mean, there could be slight variations, but you see how really, for a direct proof, everybody's proof pretty much going to look the same. You're going to start off with P, suppose P. You're going to end up with, therefore, Q. You're going to unravel these 2 definitions, and then really the only thing that might be different is 1 or 2 lines in here. But mostly it's the same. It's going to be the same type of proofs. Okay? Any questions about that? I think you guys could try a couple of proofs over the weekend. All right, so then homework. I believe I posted on Blackboard. It's on page 98. Number 2 and 3.
Due Monday or Wednesday?
We have class Monday, right? Yeah, so it's due Monday. And we'll don't have a quiz. We'll go over it on Monday, and we'll have our quiz on Wednesday of next week. Okay. Now, so you guys know that all the odd answers in the back of the book. why would I assign number 3?
It's probably a little bit worse than number 2.
It might be. They're about the same level, right? 2 and 3 are about the same level. So I don't mind if you go back in the back book and read a well-written proof, right? Remember what the goal is I said at the beginning of the day? I want you to learn how to write proofs. So wouldn't it, I mean, it's not going to hurt you to read a well-written proof. Because you'll see the ways, the structure, the wording, the phrasing, you'll see all these things. You'll see how they unravel definitions and so on. Now, so it's not bad if you decide to read it. I want you to try to do it without looking at the back of the book. But if you do number 3, and then maybe you get stuck. Maybe you're ready to give up. You got stuck. Maybe you can talk to somebody in class, talk to me. But if you want to go to the back of the book, you can use that as a help. But it'd be kind of neat, I think, to see how your proofs are right now, and then compare it to the professor who wrote this book. See how different it is. Maybe it's like eerily the same, and that shows you that you're really on the right track. Okay. So I don't mind assigning these odd number proofs. But I mean, typically, it'd be great if you did it without looking at the back of the book.
So we're only going to use the definition we got today in class.
Yeah, you don't. I'm not going to assign a homework problem that uses a definition. There are some problems in chapter 4 that use definitions from chapter 3, but I'm not going to assign those. Okay, maybe for homework or for extra, or for your own benefit.